Now let's put everything together. As I said, all over are the shouting. So, we have the conditional probabilities for the cases at hand. Let's reassemble the probability of winning by appealing to total probability, eliminating the cases 2, 3, and 12 where we lose in the first trial. We've got a simple expression. And now let's just plug in for the terms in the conditional probabilities. And we've got now the following expression. Recall, the pk squared in the numerator arises because the conditional probability is pk over pk plus p7, and it is multiplied by pk, which represents the probability of throwing k on the first trial. So you get a k on the first trial, a k on the last trial, that gives you a pk squared. It's a simple expression, and all these numbers appear in the table on your left. Right? We simply read them off and write them down and do a numerical evaluation. And let's proceed. We can simplify this a little bit by observing that the probabilities appear in pairs. P2 and P12 are the same, P3 and P11 are the same, P4 and P10 are the same, and so on. So these probabilities appear in pairs. And by grouping these probabilities, we find 6 and 36, this is P7, 2 and 36, this is P11. And then for P4 is doubled in P10, P5 is doubled in P9, and P6 is doubled in P8. So you get twice 1 over 36 times the expression in the round brackets. Okay, there's a simple fraction, we can simplify it. At this point, we've exhausted all the probability intuition. We should pause before we do anything further to take stock of what we've done. This is elementary, but there was some subtlety here. There were two appeals to additivity, to partition the space. The first appeal by what happened on the first step. The second appeal to additivity by partitioning based on the number of trials in the experiment. And there was an appeal to independence, which said that individual probabilities were obtained by simply multiplying atomic probabilities for the individual trials. Once you've got all of this, you've got a numerical answer, but of course we don't want to leave it like this. We should compute it, and we do. And we find, there's a fraction. Of course, we should evaluate the fraction because by itself it doesn't say very much to us. And we find, this is interesting, the answer is 0.4929 recurring. Now, this is interesting. Now, numerically, it's just a number. It's a probability, a chance. But let's take stock of what this is saying about the experiment itself. Remember, this is a gambling game. You've gone to the casino to gamble at craps. You've thrown dice, and eventually you win or lose. Now, this tells you that winning at craps is almost a fair coin flip. It's almost a 50-50 proposition. That's interesting. But here's the rub. It's almost a 50-50 proposition, but in fact, it is biased away from one half, below one half. This explains in part why the rules of the game are so peculiar, so arcane. There's nothing magical about the way the rules were designed. They were designed to get a chance near one half, to tempt the unwary gambler into playing more, because clearly in a game which is acutely unfavorable to you, well, you played once, twice, you find you're losing all the time, you won't play it again. But if you win almost half the time, you might feel, I could make a killing here, if I'm just lucky. This tempts a gambler to play the game. But, and here's a rub, the odds are biased against you, albeit by a small amount, but they are biased against you. In a long run of games of craps, you will lose your shirt. Okay, this again explains why the game is designed the way it is. It is to make it interesting to play while guaranteeing a built-in edge for the casino, for the house. Now, in other gambling games, the house gets an edge by simply charging a commission per game. But in this game, the edge is baked into the game itself. This is a political age, and again, we should come up with a moral, a slogan, a summary. And here it is. Our slogan, don't gamble. The other guy always knows more than you do. This principle was put in much more memorable words by Damon Runyon in her short story, The Idyll of Miss Sarah Brown. In her father's advice to her son, and I cannot resist quoting from it. "Son," the old guy says, "no matter how far you travel or how smart you get, always remember this. Somewhere, someplace," he says, "a guy is going to come to you and show you a brand new pack of cards on which the seal is never broken. And this guy is going to offer to bet you that a jack of spades will jump out of the deck and squirt cider in your ear. But son," the old guy says, "do not bet him, for as sure as you do, you are going to get an earful of cider."